All right, here we are, our first Zoom session of the semester. So we've got a very complex topic to do today, which is chapter 15. And that is our introduction to regression analysis, as it turns out. So while it's going to look kind of scary today, just be aware that a lot of the work that we need to do can be done with our calculators. So it won't be as bad as maybe it looks today. We have to set the background today, and we have to introduce a lot of new concepts and introduce some new terms. But at the end of the day, we're going to end up using our calculators to do most of the work. Our main job will end up being interpreting the results. So let's go open up 15. Now, this is actually 15A. There's actually three parts to this, 15A, B, and C. And when we're done with these, we're basically done with the course material. And then we can do our problem sets and our reviewing and our sample final. And then we can have our exam on whatever day you've been scheduled for. So when we get back, we'll have 2 weeks. And so that should be plenty of time to finish all of this. All right. And also, couple of things. This is being recorded, so I'm going to post the recording on Blackboard and also on my own YouTube account, which I set up during the COVID because all my classes then were online. And so you shouldn't have any trouble finding it. And look at all this stuff I put in there. All those class notes. Oh my God, there's so many. But so you'll be able to watch this if you want to. This is especially important for the people who couldn't make it today. Everyone else, you don't have to watch it again unless there's something important that you think you missed. Also, I'm going to be writing on the actual computer, not directly on the screen. I have a tablet here that lets me actually write directly on the slides as if I were using a whiteboard. And so those notes that I'll be creating today, I'll also be posting them on Blackboard so that when I'm writing, you'll see it when you open up Blackboard, the original slides that were not written on and the ones that I'll be working on today. So that way, no matter what happens, you will be able to find what you need. You'll be able to watch the video if you want, and you'll be able to look at these handwritten notes if you want after we're done. Well, all right then. So first things first, what exactly are we doing in this chapter? You may have heard of the name of this topic, regression analysis. It's heavily used in research, especially in areas like finance and economics. In fact, if you were an economics major, you'd be doing this all the time. It is a method for analyzing the relationship between two variables. That's really all that it is. Specifically, we're interested in both the strength and the direction of the relationship between two or more variables. And so first things first, let's look at a quick example. What if, for example, you're working in the marketing division of a corporation and they would like to know if the money they are spending on advertising is actually helping. They'd like to know how much each extra dollar of advertising is contributing to their profits, for example. They can easily do this with regression analysis, because that's what it's designed to do. We're trying to estimate a numerical relationship between two variables. Once that's done, we can now go ahead and do forecasting with our results. If they wanted to know, for example, based on past history, if we spend $100 million in advertising next year, what kind of addition to our profits can we expect? And so it's a very helpful way of explaining relationships, but also doing forecasting into the future. All right, now there's two basic types of regression analysis. The first one is what chapter 15 is all about. The second one, multiple regression, we will not be doing this semester because, first of all, there isn't enough time. Secondly, it's much more complicated. And thirdly, the calculators do not have the facilities that they need to carry out multiple regression. So we'll stop with simple regression. That will be quite enough. Once you get past that point, you would probably end up using Microsoft Excel or some specialized statistical software anyway. So this is really as far as we can go with our calculators. So what's the difference between the two? With simple regression, which is used most of the time anyway, we're going to assume that there are two variables such that one is dependent variable, which is y, and an independent variable, which we call x. What we'd like to know is whether or not there's a linear relationship between the two. If so, we can use regression analysis to estimate that relationship. If not, we have to try something different. So here's a quick example. Now, this is something you've seen before. I've just randomly chosen y equals 3 plus 4x to remind ourselves how this works. You'll recall that y is the dependent variable, x is the independent variable. And in the equation here, you can see that 3 is the intercept and 4 is the slope. Okay, it's written this way. In general, it's usually written as y equals mx plus b, where m is the slope and b is the intercept. Okay, and the slope is simply the coefficient of x, and b is a constant. So you can see what this means for our example here, y equals 3 plus 4x. 3 is the intercept, which simply means that the line crosses to the vertical axis at the point 0, 3. Okay, so in other words, when x is 0, y is 3. It's the slope that's usually the more interesting of the two. That's normally what we're more concerned with. What does it tell us here? Well, by having a slope of 4, what it really means is that if x goes up by 1, y goes up by 4. If x goes down by 1, y goes down by 4, and that never changes with a straight line. Okay, if it's a linear relationship, the slope is a constant. All right, so that, I know we already knew all this, but it's good review. Now, because we're assuming linearity when we run a regression model, it might be a good idea to make sure before we do anything else, if our variables really are linearly related to each other. So how can we determine that? Well, we can create a very special kind of graph, which is known as a scatter plot. And I'm sure you've seen these before. What you're effectively doing is you are taking data, and for both X and Y, that is. And so for the case of sales and advertising, you can see that these points represent, each point represents a single year's sales and advertising. Now, if you notice, Y is on the vertical axis, sales is on the vertical axis because we assume that sales depends on advertising, not the other way around. So sales becomes the Y or independent variable. No, sorry, what did I say? Y, sales is the Y or dependent variable. X is the advertising or independent variable. Each point is a single year. The observation, for example, that one I've labeled there is the 2020 sales and advertising. And so we gather up data and we plot them on this particular graph. And what we're looking for is to see if there is a straight line which explains this relationship. So I've drawn one in there, and it has a special name. It's called a trend line. And you can see we can get a lot of useful information out of this trend line. First of all, you notice how close the points are to this line. So it looks like our relationship is at least approximately linear. Secondly, we notice that the relationship itself is such that when X increases, Y also increases and vice versa. So we say that the relationship is positive or direct. The only thing that's missing is we don't know the strength of this relationship. In other words, we don't have any numbers yet. We don't, for example, know how much Y goes up when X goes up. That will come later. Okay, when we provide the data, we run our regression model, it'll tell us exactly how much each change in X translates into a change in Y. By the way, if you notice here, though, the points are not directly on the line. Oh, now that's interesting. That type of relationship where there can be scattering about the line is sometimes called a probabilistic relationship. And that makes things more complicated for us because we know that while there is a strong relationship here between these two variables, it's not perfect. Okay, and that's how you know, because you see the points are not directly on the line. Compare this to, here it is. Let's say the relationship between the temperature in Fahrenheit and Celsius. So if you look at it carefully, you'll see that this is nothing but a straight line, where the intercept is 32 degrees and the slope is 9/5, which means that every time this temperature in Celsius goes up 1 degree, the Fahrenheit temperature goes up 9/5 of a degree, or 1.8 degrees. And that never changes. There's no exceptions. You notice how there's no points scattered around that line. All the observations are directly on the line. It is a perfectly linear relationship. Okay. And so something like this is often referred to as a deterministic relationship, because there's no scatter of the points around the line. They're all directly on the line. Now, that would be ideal, but that's not usually how it works out in practice. We usually end up with one of these probabilistic relationships. So that just means we have to be careful. Oh, what was that? Yeah. The thing, with something like this, we ideally would all like to be muted, unless you want to ask a question, then you can unmute and then we'll hear your question. But otherwise you should keep it muted, because otherwise we'll hear the background noise. So if your dog suddenly starts barking, for example, this will prevent that from being heard. Okay, so let's get this out of the way. All right, now, so with all that being said, we're going to focus our attention on simple regression analysis, which simply means there's only one independent variable, or you can think of it as 1x. So let's say that we've decided that sales revenues depend only on advertising expenditures, and we want to know how strong this relationship is. Or think of it this way: we want to know how much each extra dollar worth of advertising adds to our sales. We can easily analyze this relationship with simple regression, because that's exactly what it was meant to do. On the other hand, if we think that maybe our sales depend on not just advertising, but the prices that we charge, that's a different matter altogether. Because now all of a sudden, we have two independent variables. You can see them on the top. Sales are now assumed to depend on X1, which is advertising, and X2, which is prices. That type of model would require multiple regression for us to implement it and then analyze it. So again, that's the kind of thing we won't be doing here. Our calculators can't do that. And we don't have that much time left either. So it's enough to be aware for the time being that multiple regression is used when we have two or more independent variables. All right, so that's the distinction between the two. So we'll be focusing all of our attention on simple regression analysis. Yes, this notation I'm sure you're very familiar with. Y is a function of X. Again, Y is the dependent variable, X is the independent variable. Okay, so we've seen this. Now here's another quick example. It's pretty clear, or should be clear, that if you're analyzing the relationship between height and weight, weight clearly depends on height. It's not the other way around. So in that case, weight would be your dependent or Y variable. Height would be your independent or X variable. And therefore, we can write this as weight is a function of height, which implies that weight is Y and height is X. How do we analyze this relationship? Well, obviously, we need sample data. We gather a sample, and what do we do first? We use a scatter plot to determine if the data are linearly related to each other. So let's say this is what we end up with. Okay. And by the way, if you notice, when both variables have,
do you have anything later or no? Are you doing anything?
Let's see what we can do about that.
To what? That's corny as hell. I've never went to one in my life.
Oh, there he is. All right. All right. So anyway, here's our trend line for the weights and the heights. You notice what I've done. The line itself, I basically just drew it just where it appeared to be close as possible to all the points. The interesting part about regression analysis is how does it find the line that gets as close as possible to all the points? That's really the complex part. That's where all the hardcore math gets involved. Exactly how do we find the line that fits to the data better than any other? So we'll get back to that later on. But right now, I just want you to see that there's a positive slope, which means that, of course, as taller people on average should be heavier than shorter people. And we also, once we have the actual data, we can figure out exactly how much being taller adds to your weight compared to being shorter. We also see that it's a linear relationship, so we can feel free to use regression analysis. Now, here's one of my favorite examples. This involves stock returns. You'll run into this a lot in your finance class next spring. What we're doing here is we're comparing the rates of return to Apple stock and this very special stock index called the Standard & Poor's 500 or S&P 500. It's something you may have heard about in your travels. Basically, what it is it's an average that represents the prices of the 500 largest American stocks. It's very widely followed on Wall Street because it reflects very closely the state of the economy. In fact, if you wanted to look it up, any of these many websites that's geared towards investors will have it there. So for example, let's look at CNBC. And you see they're all on the top here. The Dow Jones Industrial Average is down a little. The Standard & Poor's 500, it's down a little, not that much, 11 points. The NASDAQ, which is all the high-tech stocks. And then Russell is, I think it's the largest 2,000 stocks in the United States. And the VIX is a volatility index. That's what this number represents. And so everybody has their eyes on this all the time. Because if it's going up, people start to become more optimistic, and then stock prices tend to rise too. Other stocks, I mean. If it's going down, people get nervous, and then maybe they start selling their holdings. So everybody has their eye on this number every single day. At least people are involved in the markets. So Apple, on the other hand, now Apple's a single stock. As you can probably imagine, its returns are heavily affected by the state of the economy. I mean, it's a great company, but if the economy is slumping, it's going to hurt their sales. There's just no getting around it. So what we'd like to find out is the connection between the returns to Apple and the returns to the S&P 500. So based on the results there, you can see that the trend line has a positive slope, which means, as you would expect, that when the S&P 500 goes up, Apple goes down, up rather, and vice versa. Also, if you notice this time, because these are returns can be negative. So the points now are not restricted to the first quadrant. That's why they can go all the way down here. So when you have both positive and negative values, you end up with something like this. Okay. And ultimately, when you do get your final results, you'll be able to tell how much, what percent change in the returns to the S&P 500 will affect the returns to Apple. Multiple regression. Let me show you a quick example of a multiple regression case. Imagine that you're an economist now. You're working on Wall Street, and you're analyzing 90-day Treasury bill yields. Now, as you probably know, the U.S. government runs up massive deficits every year, and they have to cover those. They have to pay their bills too, just like the rest of us. Where do they get the money from? They borrow it. They do that by issuing Treasury securities, such as 90-day Treasury bills. The yields in those reflect the state of the economy. Okay, when the economy is booming, we tend to see relatively high interest rates. When the economy is slowing down, we tend to see lower interest rates. So we want to know how much the Treasury bill yields are affected by the growth rate of the money supply and the growth rate of real GDP, which is basically the size of the entire economy, or the dollar value of how much output has been produced in the past year. Well, obviously, we now have more than one independent variable. In fact, we could think of the treasury bill yield as Y, the dependent variable. And then these two could be considered, we'll call them X1 and X2 now. X1 is the growth of the money supply. You must have learned about all this in macro. X2 is the growth rate of real GDP. Okay, we could easily analyze this relationship with multiple regression, but that would require a very sophisticated tool like Excel or possibly statistical software. So sadly, we won't be doing that here, but it's good to know that there is such a thing as multiple regression. And also, you can't really draw the relationship when there's two independent variables. I mean, you can try. You can see what I've done here. I've got three axes, Y, X1, and X2. And instead of having a straight line, you'd have a plane. But I did my best here. It's not terribly helpful to see that relationship. But that's graphically, that's how you would show the relationship between two independent variables and one dependent variable. All right, now we're ready to focus our attention on linear relationships. And again, we all know this very well. The equation of a straight line is y equals mx plus b. M is the slope, b is the vertical intercept. And how do we interpret those? As we said earlier, B is actually the point where the line crosses the vertical axis. That would be the point 0, comma B, because x is 0 then, and y equals B. You can think of that B as the value of y when x equals 0. And then the slope. The slope is the interesting one. This is the one that we normally are interested in. It's very rare that the intercept is very important, but you never know. But here our focus will be on the slope, and the slope is defined as the change in y over the change in x. Formally, it's written as delta y over delta x. Or you might remember in high school, sometimes they call it the rise over the run. Okay, so this is a rise, and this is the run. Yeah, that's not very formal though. That's informal, just to help you remember what it looks like. But basically, it's delta y over delta x, and that's what we're normally interested in with regression analysis. Or you can think of the slope as the sensitivity of y to changes in x. And again, the intercept b is simply where does the line cross the y-axis. All right, so I used Excel to actually come up with some more scatter plots. Just we'll take a quick look at these. This first one is very obviously linear, or it's very close. It's as close as you're going to get with real data. All right, look at that. They're almost perfectly lined up. This is as close to perfect as you're going to get with real world data. For this data, we have no trouble running a linear regression because clearly the assumption is being met very well. But let me show you an example where the data are not linear. And you'll say, wait a minute, what's going on here? Well, if you notice, it's a curve. Specifically, this one is known as an exponential trend as opposed to a linear trend. And the key detail here is that the slope of this curve is getting steeper as x increases. Now, this would actually be a good model of, let's say you put money in the bank at some point and locked in a specific rate of return for this next so many years. The balance in your account would look something like this, because at first it would grow very slowly, but as your interest starts to pile up, the balance will grow very quickly in the later years. And so this would be a very good reflection of what is going on in your bank account, but it's not a linear relationship. Okay, and that's good for the investor. So if this was the data you were using, you would not want to use linear regression analysis because it's going to give you terrible results. Like, for example, it would try to fit the points and you'd end up with something like this. And you can see, well, that's pretty bad. So we would say, no, let's not do that. All right. Now, we're going to start by introducing some notation. Just as a quick reminder, normally in statistics, we do not have access to all the data in a population. Or even if we do, it may not make sense to try to analyze the entire population when a sample will do just as well. So normally we use samples to estimate the properties of a population. For example, early on in stats 1, remember that X bar, which is the mean, sample mean, was used as an estimate of the population mean mu. So what does this have to do with anything? Well, here we're going to assume that there exists a population regression line which best fits or explains the data found in the entire population. But unless we have the entire population available to us, we can't actually calculate this population regression line. What do we do instead? Instead, we're going to use sample data to estimate a sample regression line. So this next section is going to help us learn about the notation that will be used for the sample and the population regression lines. It's a little messy, but we'll get used to it very quickly. So first, let's look at the equation of the population regression line. And let's try to make sense out of it. Here we go. So there it is at the bottom with all that writing attached to it. That's what it looks like. That is the equation of a population regression line. Now you can tell that it must be a population measure because of all the Greek letters. Now that fancy B is actually the Greek letter beta, and the fancy E is the Greek letter epsilon. Notice there, instead of having two separate letters, though, for the intercept and slope, most books just call it beta 0 and beta 1. It's just easier that way, because then you can expand it to include the possibility of a multiple regression line. Also, if you notice, the variables are indexed. Why are they indexed? We haven't seen that before, because each point could potentially at least have a unique error term attached to it. So epsilon I is the so-called error term. What is that doing there? It's there to reflect the fact that the points, even in a population regression line, are mostly not directly on the line, but either above it or below it. So we have to measure that by keeping track of every single point in our population and attaching to each one an error term. So you'll see more about that on the next slide. It'll be easier to visualize it with a graph. All right, so again, the two differences here between this and an actual straight line, the traditional equation of a straight line, yes, it has an intercept and a slope, but suddenly there's this error term in there, and the variables are indexed. Wow, already you can see it's getting a little intense here. That's right. So let me show you the graph on the next page. All right, so as I was saying before, yes, we have a straight line here, but that's the trend line. The data are the points. And so for point 1, now if you notice, this ordered pair is labeled x1, y1. You can think of it as point 1, I guess. That could be, I don't know, the sales and advertising in the year 2010 or something like that. If you notice, the point is above the regression line. The regression line underestimated the true value of Y in that year. So between the actual Y and the point on the line, that vertical distance is called an error. Okay. In fact, that's what this is supposed to be. It got a little messy, but that error is the difference between the actual value of Y1 and the value that was estimated by the regression line. And you can see it's a positive number. Now let's move ahead to point 2. Oh, I forgot. I just want to clean this up a little bit. Yes, it can get a little messy. But except it's not like the board where I can erase it all. I could erase it, but I'm not going to. It has its own error term, which we're going to call it epsilon 2. Once again, it's the difference between the actual Y2 and the estimated value, but this time the regression line overestimated the value of Y. So because the error is defined as actual minus estimated, that implies that this error is negative. You can see it at the bottom there. So we've got positive errors and we have negative errors. Interesting. Sometimes the regression line overestimates the value of Y, sometimes it underestimates it. Sometimes it gets it exactly right, but it's kind of unusual. But what we are now, you might think we'd be very nervous about this. Wait a minute, it's got all these error terms all over the place. What we're hoping to see, though, is that the error terms cancel each other out. In other words, if you add up all the positive error terms and then you add up all the negative error terms, they'll exactly cancel each other out, and you'll end up with a total error for all the points of 0. If that's the case, then everything's fine. In fact, I made up a good analogy of this before one of my classes. I thought this was a good example of what this is like. Here's an analogy to this. Suppose you have a scale at home, and sometimes it overstates your weight and sometimes it understates it. As long as the errors offset each other, meaning that on average your weight is correct, you can use it knowing that it is reasonably accurate. It's never perfect, but on average, it does a good job. That's what we're hoping for with regression analysis. But what if instead, if the scale always over or understates your weight, well, then you have to adjust it. You can't rely on it. So therefore, you make an adjustment. Same thing is true here. We want to know that these are going to average out to 0. Otherwise, we have to do something. Right. Now, another question that you're probably thinking is, why are there errors? Why aren't they all just sitting on that line? Wasn't that the case with Fahrenheit and Celsius? Yes, but that's not real world data. That is a definition. Scientists define Celsius the way I showed you, and therefore it always holds. It's not subject to real world problems, and in any more than comparing or determining the distance in kilometers from the distance in miles. It's a perfectly deterministic relationship. Here, though, we're looking at the real world. So what's causing this? Well, number one, when we only have a single independent variable, it may just be that we're missing something important. For example, if we try to claim that sales depend only on advertising, what if that's not true? What if other things affect our sales, like interest rates or oil prices? None of that appears in our model. And therefore, the fact that the points are scattered around the line might reflect those other variables. Number two, the data itself may contain errors. Suppose that somebody gathered up that data and they made a typo when they entered it into their Excel spreadsheet. That's going to cause problems too. Number three, some of the violations of regression analysis. What I should have said here is, I think this is not what I meant. There we go. Some of the assumptions that we're making when we do this are not true. For example, what if the relationship between sales and advertising is not really perfectly linear? Like let's say that up to a point it's true. But when advertising gets to a certain point, it has a progressively smaller impact on the sales. In other words, there's a saturation effect. When people see certain commercials on TV too often, they start to tune it out. And so that means that the line could start to flatten out after a while. Then it's not really linear anymore, is it? If that's actually happening, that's going to cause error terms with our results. So therefore, it's not surprising that there are error terms in our data, because the model that we're using to explain these variables is not perfect. So, but as long as we're aware of this, as long as the errors themselves average out to zero, it's not a real problem. Just like the scale, we know that it's never exactly right, but as long as it's on average correct, we're good with it. And then, by the way, I've got another graph with some more examples of errors. We might as well take a quick look at it. Here we're looking at the relationship between weight and height. So for 0.4 over here, you can see the error is positive because the actual y is above the estimated y. Actual y4, estimated y4. Ooh, that's a big difference. Then for 3, way up in the top, same thing. This is 0.3. And this time, the actual is down here somewhere. The estimated is up here, and therefore the error is negative. Okay. So as long as, again, they're averaging out to zero, no, there's no problem here. Okay. By the way, what if that wasn't true? What if the errors did not average out to zero? Let me show you some more graphs. In the bottom left-hand corner here, they do average out to zero. Wonderful. But look at this one in the upper left-hand corner. Oh my God. That regression line is really terrible because the points are almost all below the line. Means the average error is negative. On the other hand, the one on the right, look at that. The line is almost below every one of those points. So the errors average out to a positive number. So that means that in these first two cases, you cannot run your regression without making any adjustments. Otherwise, the results will be pretty far off. So one in the bottom left that we're fine with. Okay. And the indexing, yes, we mentioned that before. All right, so one more thing. Now, this is where it really gets interesting. The regression line itself is actually a series of centers of probability distributions. Oh my God. Those red curves are sideways versions of the normal distribution. The centers are on that line. So if, for example, your actual point is way up here somewhere, this is your error. If your actual point is down here somewhere, this is your error. So we're assuming not only do the errors average out to zero, but the errors themselves, if you notice, follow the normal distribution. Now it's really getting deep. They follow the normal distribution. And each one is assumed to have the same standard deviation. So each error term, just throw this in here. Yeah, that came out of the book. There's no way I was going to be able to draw this one. Look at that thing. By the way, I guess you already start to get the point that a lot of these terms make very good fill-in questions. So in other words, yeah, we're going to do a lot of the work on the calculator, but you never know when you might be asked to define an error or something along those lines. So the errors themselves, the errors can be thought of as random variables that are normally distributed of zero and a standard, well, the standard deviation we don't know, not the data, but which is equal or the same for all error terms. So whatever it is, it's the same for all of them. Man, that's a lot of assumptions. Now, what I'd like to do is show you a graph that I put together, which shows you what happens when that's not true. The one on the left, the standard deviations are the same. The one on the right, they're not. How can you tell because of how spread out the curves are? They're all centered on the line, of course, but this one has a very high standard deviation. This one has a very low standard deviation. So here they're all different, and this is exactly what we don't want. Okay, the one on the left is fine. That's exactly what we're hoping to see. The one on the right is a nightmare. We don't like that one because it'll affect our results. Also, oh, here we go. Let's start looking at the assumptions of regression analysis. These are the things we're assuming are true. If not, the results are less accurate. But fortunately, as it turns out, sometimes there are steps we can take to offset these problems, although I don't think we'll have time to do any of them this semester. Number one, as we've already discussed, for each of our x's, the corresponding error term is normal with a mean of 0 and some standard deviation sigma, okay, which in turn is assumed to be the same for all the x's. Now, by the way, another graph I've drawn for you is to show you the distinction between the cases where on the left, the standard deviations are very low, and on the right, the standard deviations are very high. Between the two of these, which one would you have more confidence in? Well, I would say the one on the left is something you could have a lot of confidence in. The one on the right, I wouldn't say so. So the standard deviation affects the quality of our results. A high standard deviation means the model is just not very good. A low means it's very good, very reliable. All right. So the second, we're assuming the standard deviations are the same for every X. Also, I don't know why this is, you wouldn't think this would be a problem. What they specifically are telling us to assume that the error terms are standard deviations are also finite. It's not enough apparently to say that they're the same. We have to specify that they're not infinite. All right, whatever. And then number three, I'll give you a minute to catch up. Error terms are soon to be independent of each other, which means if you plot them out, there's no pattern to them. Well, once again, I have a graph for you or a diagram that shows you the difference between error terms that are independent and the ones that are not. So let's try this. The one on the left, the points are pretty much randomly scattered around the regression line. And so there's no pattern to the errors, and that's what we're assuming. Look at the one on the right. What happened here? On the left, we have all these positive error terms all in a row. Then all of a sudden they switch to negative, and it's all negatives after that. So there's a pattern there, isn't there? So therefore, there's something going on. There's some relationship between the error terms, which means they're not independent, and that's a very bad sign. Wow. Okay. So now we're going to start to at least mention the technique we'll be using to estimate our regression line. The technique we're using is called ordinary least squares, OLS. Now, why do they call it? It sounds very demeaning. It's ordinary least squares. No, it's called that because this is the one we use the most often. It requires the fewest assumptions. So we use it quite regularly unless one of our assumptions is violated. Then we need to try something else. So in general, we use this OLS unless there is a major violation, keyword there's major, of the assumptions of regression analysis. All right, and in this course, we're only going to use OLS, but you should be aware that there are other approaches that we could take. Now, later on, we'll see the formulas, but right now, I just wanted to show you the formula or the equation after all this time of the sample regression line. We've already looked at the population regression line. Now we're going to introduce finally the sample regression line. Let's take a look and see how they're different. All right, so what do you notice? Well, first of all, because this is a sample regression line, we're going to be using Roman letters instead of Greek letters. So beta 0 becomes B0, beta 1 becomes B1, and that's easy. What happened to the Y? What is that pointy thing up there? Well, that punctuation mark is known as the caret. In statistics, we always use it to represent an estimate. So here, what we're saying is that the estimated value of Y, or Y hat, is an estimate of the true value of Y, which is in the top here. And then finally, the epsilon has disappeared. Because it's supposed to be equal to 0 on average, we don't estimate it. If we did, it would simply be 0. Our estimated or average value is just 0. So it drops out of the equation. And so we're left with a real, this is a true straight line, because you can see this is our intercept. And this is our slope. Well, what do you know? Okay. So the question then becomes, well, where do we get B0 and B1? Well, I'm going to show you the formulas. Oh, I'm sorry, I missed the chat. Oh, no, I'll go back to it right now. Hold on. Sure. No, absolutely. Plus, yeah, these slides are going to go up the way you're seeing them now. They're going to go up in the Blackboard anyway. So if you did miss something, that's fine. But if you, yeah, no, absolutely. Let me know if you missed something. Oh, you're good. Okay, great. Um, yes. So anyway, this is what's going to pop out of your calculator when we start using them. We won't have time today. When we get back from break, we'll be doing plenty of examples. We'll be putting the Y's and the X's in our lists. And then what will happen is the calculator will not only show us the regression line, but several key statistics that we'll need to test the quality of our results. And that includes at least one hypothesis test. So that, don't worry, that's coming down the road, not today. But that's, so the calculator can do a lot of the stuff for us, as I was saying. But we have to understand what it's telling us. So now, one more thing I do want to mention here, even though the error term dropped out, we have to be aware that the epsilon is a population measure. There's supposed to be subscripts. Yeah, that's one of the annoying things about PowerPoint. Sometimes making subscripts can be a real headache. It's just determined to be a pain in the butt. Yeah, I don't know what the problem is. I'll just have to leave it like this for now. But anyway, so the error term that we've been using, epsilon I, has a corresponding sample version called EI, which is not called an error term any longer. It's called a residual. Okay, now we're going to use those in a very important way. Oh, sure, go ahead. We're going to be wrapping it up very soon anyway, because there's certain things I just would rather do in the classroom. And so we're getting close to that point right now anyway. So you might as well just take off. And plus next week, I'm going to review all this stuff with you anyway. This can't be enough. I'll have to go back and just completely review everything we've done today because it's pretty involved, as you can see. So that's okay. Besides, it's a doctor's appointment. That takes precedence over everything else. All right. Let's see, where are we? Oh, yes. So we're going to see a lot of that. The residual. The thing about the residuals is that they give us an important clue as to whether or not our regression line makes sense with the data that we have. It's a good way to test the results. And so we'll see, it'll prove to be a very important idea, but let me just quickly show you a graph where you can see what residuals look like. You can see it's just like with the errors. It's exactly like with the errors. This one up here is a positive error because it's defined as the actual y right here minus the estimated y. This one is negative down here for the same reason. Actual is down here. And estimated is this one. So you can have positive residuals and you can have negative residuals. But again, we have to make sure that they're averaging out to 0. Otherwise, we have big trouble on our hands. Wow. All right. Now, here we go. This is what we've been building up to in this section, at least. The equations that we'll use to run our regression. Okay, you too. Have a happy Thanksgiving. What we're trying to do with our regression line is keep the residuals as small as possible. Okay, that's what we're trying to do. Mathematically, we're trying to minimize those residuals. Now, unfortunately, if our assumptions are met, the average of all those residuals will be 0, no matter where we put the line. So instead, what we're going to do is minimize not the sum of the residuals, but the sum of the squared residuals. This we want to be as small as possible. Okay. It'll never be perfect. It'll never be 0, but we want it to be as close as possible. And that's the formal way in which we define a regression line, at least a sample regression line. How do you like that? So let me just show you a quick graph here. And what you'll be able to see is that it's pretty obvious which one we would like to choose. By the way, don't forget this y is these are the actual y's. This is the estimated y, the one on the line. That's what we mean by residuals. So by squaring them and adding them up, that number needs to be as small as possible. So let's say here in this last graph, let's say there's 2 lines, A and B. Which one would you pick? Obviously A. Well, how would you be able to compare the two? Because the top one has the smallest sum of squared residuals. This one, with this one, the sum of squared residuals is the largest. So therefore, we avoid it. Okay, so I think we've all had enough of this stuff. And again, we'll review it We're not just going to let it sit here. I mean, this is a lot of complicated material. And so we'll run through it one more time next week, and then we'll start doing some actual problems with the calculators. But I'm also going to show you how to do this in Excel, because it's a very valuable thing to be able to do. And it's only going to come in handy in your future business classes. So don't be put off by all this. Don't go to Thanksgiving dinner worrying about, oh my God, this stuff is so complicated. We'll get used to it in small stages, and you'll see that the calculator will do a large percentage of the work for us. So why don't you just go off and have fun, and then have a great Thanksgiving, okay? And I'll see you all next Tuesday.
Thank you. Have a good break.
All right. You too.
Thank you, Professor.
Bye.
Have a good break.
See you
Thank
later.
you.
Thank you.
Bye.
Thank you. Have a good break.
You too. Bye.
Thank you.